Good evening, everybody. Welcome to an evening of Chem 1105 with your host, me, Dr. White. Today's session will be the review for test two. And let me remind you, this Thursday on the 14th, I will be giving test two online at 8 o'clock a.m. or earlier, probably a little earlier. I'll send out an email with the password that will allow you to open test two PDF file, which will be in the assignment area of Blackboard. Should take you about 40 minutes to finish the test, but take 3 hours. If you need an extra half hour, go ahead, take it. However, please make sure that you have your test number two answers uploaded to the assignment area Blackboard by this Friday, 8 p.m. as a single PDF file. All right, you'll need a scientific calculator. I sent out an email where I showed, where it's a video of mine, how to use a scientific calculator. Test two, excuse me, will cover chapter 4 and chapter 5, part 1. This covers chemical bonding, including ionic and covalent chemical bonds, and it will cover mole and mole-related topics, and it'll have balancing chemical equations, which hopefully you've done the practice problems. There'll be 18 problems, 9 pages. There are no multiple choice, but some of the questions are multiple part, just like the practice problems. Oops. And topic breakdown, chemical bonds and related topics, 50 points. Moles and mole-related topics, 55. That adds up to 105 because there's five bonus points. Am I nice or what? Don't answer that. All right. And I reserve the right to subtract up to 50 points. Anybody doesn't follow instructions. And anyone who does not upload your test, that should be test two, not test one, on time as a single PDF. And here I have one, I'll be posting it. And next Monday, I will go over the answers in a Zoom meeting at 8 o'clock. All right. Now, important thing about test two, like test one, underneath your name, it will say, please use proper significant figures for all calculated answers. And it'll also say, please use three significant figures for all atomic masses. I'll say it again. Underneath your name for test two, it will say in red, so you don't miss it. It will say, please use proper significant figures for all calculated answers, and please use three significant figures for all atomic masses. And what does that mean? Well, you know about how to calculate significant figures for mathematical operations, multiplication, division, addition. Now, if we look at our friendly neighborhood periodic table, which this is right there, you'll see hydrogen here has 1.008 as the atomic number. That's the number underneath the element symbol. And that's four significant figures. So how do you round that off to 3? Keep the 1, keep the 0, keep the 0. Use the 8 to round off. Is that 5 or higher? Yep. So you drop that and the number in front increases to 1. So the atomic weight of hydrogen, the three significant figures is 1.01. I'll help you out. Oxygen, 15.999. Three significant figures. I'll give you a couple seconds to try it on your own. Time's up. And the three significant figures, oxygen is 16.0. And you should do that for all the different elements we use in the periodic table. This one, which you'll be given. It'll be a download you can get from Blackboard in the test assignment area for test 2. All right. Now, one thing I do want to show you, if you go to the course information in Blackboard, lecture folder, and if you scroll way down, you'll see test number 2 review, both as a Word document and a PDF file. And if you scroll down even more, or scroll up, I passed it, you'll see important information, test number 2. I guess I didn't put it as a PDF file. I should have. And this is the information. This page will be at the back of test number 2. Years ago, before I changed my thought on how much a student should memorize in my class, you would have to memorize everything on this page. However, this will be given to you. All right, let's start with the review. And this file you can find on the lecture, in the lecture section, like I just said, of Blackboard. All right, things you should know. First of all, you should know what a Lewis structure is. A Lewis structure is how you show the valence electrons, the outermost electrons of an element. And you put one dot on each side for each valence electron, and you get one on each side before you double up. You never have more than 2 on a side, and you never have one side with none when others are doubled up, one on each side. And as you hopefully remember from test 1, the number on the top and here in red, or the Roman numerals, is the number of valence electrons. So if I were to ask you, do the valence electrons for, let's do argon. Argon AR has 8 valence electrons. Let me get my tablet at the right angle. And you have argon, 1, 2, 3, 4. And now we start doubling up, 5, 6, 7, 8. And that's the Lewis structure for argon. Now, next I started talking about the fun stuff, chemical bonds. And you should know there are 2 types of chemical bonds, ionic and covalent. And you should know, this is a definition you should memorize. What is an ionic bond? It's the results of a transfer. It's the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. That's an ionic bond. You should know the definition of covalent bonds. And that's the sharing of 1 or more pairs of electrons. They're sharing. I don't know where I came up with this covalent bond time. My hands are sharing electrons. And remember, covalent bonds is a sharing of 1 or more pairs. Pair means 2 groups of electrons or electrons between atoms. Now, I talked about the octet rule, how elements, I'll never ask on a test, what is the octet rule? And that is where elements lose, gain, or share electrons such a way that they have 8 valence electrons, which makes that very stable. And one way of doing that is either gaining or losing electrons. And when an element loses 1 or more electrons, it forms a positive ion called a cation. When an element gains 1 or more electrons, it forms an ion with a negative charge called an anion. And elements lose or gain electrons that have the same number. Ooh, I misspelled this. Electronions. I just invented a new word. I tell you, I was always first down in spelling bee. But anyways, they have the same number as the nearest noble gas. Remember, elements never lose protons when forming an ion. So let's do a quick example, which I have here. I forgot I wrote it. Write the ionic formula. Oh, this is something else. All right, what ion does, well, let's pick something. What ion does oxygen form? Well, how do you do that? Well, you have to look at oxygen. And oxygen has 8 electrons and 8 protons. Remember, the atomic number in the upper right-hand corner gives you the number of electrons and protons. Now, it wants to have the same number of electrons as the nearest noble gas. We've got 3 choices. Neon at 10, helium at 2, argon at 18. Which one is the closest numerically? And neon. It's only 2 away. Helium is 6 away. Argon, which I worked with argon when I was in grad school, a lot of it, is 10 away. So 2 away is closest. And neon has 10 electrons. So how do we use that? Oxygen has 8 electrons and 8 protons. It wants to have the same number of electrons as, got a mental block, neon. I thought it was neon, but I didn't want to make a mistake. But it will still have 8 protons. So there are 10 electrons. Each electron has a -1 charge. There are 8 protons. Each proton has a +1 charge. Do the math, -10 plus 8, add them together, -2. And the way you show the charge or ion, the chemical symbol, and up here, superscript, -2, or the newer way, which I don't like, I'm old school, 2-. And either way would be, so this is the answer, what ion? And again, you tab the element, you look on the periodic table, say what's the nearest noble gas numerically. That's the number of electrons it wants to have, in this case 10. It still has the same number of protons. Each electron is a -1. Each proton is a +1. Do the math, add it up, get this, and then show it with the chemical symbol. And that's how you do it. Now, all molecules have a net zero charge. If you find an exception to that, let me know and we'll be rich beyond my wildest dreams. And that goes well beyond me getting a couple of Ferraris, Lamborghinis, my own island in the South Pacific, and a couple of fighter jets to play with. Goes beyond that. Why? Because it won't happen. All molecules have a net zero charge. So what does that mean? If I ask you to write the empirical formula or the ionic formula from the ionic charges, generally I'll ask for the empirical formula for calcium +2 and chloride -1. What do you do? Well, if you notice, calcium has a +2. And chlorine is a -1. and it has to add up to 0. Ooh, it doesn't. You can't change the charge, but you can change how many of that ion is present. So to get this to add to 2, to 0, this is a +2, I need a -2, so I'll multiply 2 times -1. So this tells me right here, the formula has 1 calcium and 2 chlorines, and you write it that way. And that's something you should know how to do. All right. And the same thing applies to polyatomic ions, where you have a group of atoms acting as one ion. All right, now, next we talked about covalent bonds. Dr. White loves covalent bonds. Ionic bonds are great too, but I did a lot more work. A lot of the research I've done is covalent bonds. And there are 3 bonds you should know: single bond, double bond, triple bond. We're in class right now. I'd say, class, what are the 3 covalent bonds? And I'd ask you to yell it out: single bond, double bond, triple bond. Now, you should know a single bond is a bond in which 2 atoms share 1 pair of electrons. A double bond is a covalent chemical bond in which 2 atoms share 2 pair of electrons. Remember, a pair means 2. And a triple bond is a bond in which 2 atoms share 3 pairs of electrons. So you should know what is the 3 types of covalent bonds: single, double, and triple, and how many pairs of electrons they share. Single bond, 1 pair; double bond, 2 pair; triple bond, 3 pair. And you should know how to draw the Lewis structures. And what do I mean by that? "80% of the air you're breathing right now," and I hope you all are breathing, if not, start breathing, is nitrogen. And if I were to ask you sometime in the future, 3 points each, draw the Lewis structure for, and the first one, A, is nitrogen gas. N2. Well, first you have to look up how many valence electron each nitrogen has. And nitrogen has 5 valence electrons. And here's the Lewis structure for nitrogen. But there are 2 of them. And this nitrogen says to this one, I've got 3 unpaired electrons, the single dots. You have 3 unpaired electrons, a single dot. Let's share. And they do. And unlike the Lewis structure of an element for a molecule, you can have more than 2 dots on a side and some 0. And notice here we have 3 pair of electrons, and that's a triple bond. I bet you didn't know when you were inhaling the air you're breathing now, the nitrogen gas in that has a triple bond going into your body. Hope I didn't scare anybody. And you should know these are called the bonded electrons. And these on top are the non-bonding electrons. Now let's do one more. And this is sodium hydroxide. a chemical widely used in the chemical industry. And the question is, draw the Lewis structure. Now, there's something important I need to teach you right now, or hopefully you learned it from my videos. Sodium has one valence electron, oxygen 6 valence electrons, hydrogen 1 valence electron. How do we know that? Well, you go to your friendly neighborhood periodic table and notice hydrogen and sodium have a 1 on top, 1 valence electron. Oxygen on top, 6. You know your Roman numeral, VI is 6. I had to write these in because a couple of years ago I realized, oh, they're not teaching Roman numerals in school. I learned that in, I think, second or third grade. I forgot which. That was a long time ago. All right. Now, here's what I want you to pay attention. Excluding hydrogen, which is not an alkali metal, the alkali metals and the alkaline earth metals, first and second column, excluding hydrogen, always form ions. They are never in a covalent bond. So the question is, what ion does sodium form? And that's a +1. You can figure it out on your own, but it's a +1, potassium +1, lithium +1, magnesium +2, calcium +2. So what does that mean? It means in sodium hydroxide, you'll form a +1 ion. Well, now you have the oxygen with 6 valence electrons, and the hydrogen with 1, and it shares it here. And if you look at this and you say, oh, something's wrong, because I didn't point out here, but I'll go to the one we did before. Atoms share and have valence electrons, so it has a total of 8 valence electrons. If you look at this nitrogen, it has 2 + 2 + 2 + 2, and that's 8 valence electrons. And the same thing with the other one. Bonded and non-bonding electrons should add up to 8, and the same thing happens, 2, 4, 6, 8. But if we look here, hydrogen's the one exception. Its octet is 2. Hydrogen's octet is 2. But here, this oxygen, we only have 7. That can't be. Well, what happened? This electron that sodium gave up to become this cation goes here. And this electron, when it becomes a cation, it gives up a +1 cation. It gives up 1 electron. It goes to the oxygen. This now has 1 extra electron, and it has a negative charge, the OH, called the hydroxyl polyatomic ion. So between sodium and the hydroxide ion, this ion, there's an ionic bond. Between oxygen and hydrogen, there's a covalent bond, a single bond. So there are 2 different types of bonds in sodium hydroxide, both ionic and covalent. And you should know that for the first and second column, except for hydrogen, they never, ever form covalent bonds. They always form ions that are and give up their valence electrons and are in an ionic bond. Well, by the way, one other ionic compound you should know, take 1 sodium, 1 chlorine, +1, -1. That adds up to 0. And that's table salt. also known as sodium chloride. And if you ever go out with a bunch of chemists, I've done this and the friends of mine have, one of us will say, can you please pass the NaCl? NaCl, never mind. All right, let's move on to the next area, and that's chemical equations in a mole. And a chemical equation shows a reaction, chemical reaction in a graphical or equation form. And here I have A plus B, meaning you react A and B together and you make C. At the base of that arrow, A and B, think of the plus sign as the word and, are the reactants. And because I have spent many decades in the chemical industry, we also call it starting materials. C, whatever at the head of the arrow, is the product. Now, I went through in the videos, and you did already practice problems, and hopefully you've done others, how to balance a chemical equation. You can only change the coefficient, the number in front. Now, my advice to you is always leave hydrogen and oxygen last when you're balancing chemical equations. And remember my even odd trick. Go back and watch the video if you haven't. Now we got into some really exciting stuff. The mole. And I'm not talking about a furry little animal that digs holes in the ground. The mole is, and you should know, is the chemical counting unit. Now, there are different ways of defining a mole. 1 mole of an element is Avogadro's number, and Avogadro's number is a number named in honor of Avogadro, Italian scientist. I don't know if they called him chemists back then, who did work with the mole and relationship of moles. And the number 6.02 times 10 to the 23rd, actually 2 German chemists, which I can't remember their names, most chemists don't, unfortunately, came up with that number, but it was renamed in honor of Avogadro. And that's 6.02 times 10 to the 23rd. And that's a calculated number. That's 3 significant figures, see 6.02. Now, 1 mole of a compound is equal Avogadro's number now in molecules of that compound. And 1 mole of an element is also equal to the atomic weight of that element in grams. And 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights in that compound. Now, all these things are an important information. Test number 2. Years ago, students in my class would have to memorize all that. What 1 mole of an element is equal to, and what mole of a compound is, those 4 things. Plus what's the molecular weight of a compound. I will give that to you. Thank you, Dr. White. You're welcome. Now, you should know how to convert moles of an element to atoms of an element, or add the reverse, atoms of an element to moles of an element. This is all in the practice problems in my videos. You should know how to convert moles of a compound to molecules of a compound, the reverse, molecules of a compound to moles of a compound. And you should use your good buddy, your good friend, and it's been my good buddy and my good friend for many, I hate to say this, decades, unit analysis. I learned it in high school from Mr. Salters, our AP science teacher. And let's look at number one. Let's just go through one because I want to show you a couple of things. When you have a word problem, relax, take a deep breath, let it out. Once you know how to do word problems, they're not scary. On a test, if I were to ask how many molecules are 6.22 moles of HCl, that's hydrochloric acid, we'll learn what acids are later. What are you being asked to find? I use a question mark, molecules of HCl. What are you given? 6.22 moles of HCl. This is the only thing we have to start with. We're trying to get to these units, molecules. And how do you use your good buddy, your good friend, unit analysis? If there was a conversion ratio, something over something, what would go on top? Units, the molecules of HCl. What do you want to get rid of? Remember, anything divided by itself becomes the number one and is gone. It's got rid of. So if I don't want moles of HCl, my answer unit-wise, I don't, I'll divide it by moles of HCl. And where do you get this ratio? 1 mole of compound to molecules. You look at important information, test number 2. 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecules of that compound. Now, 1 is an exact number, meaning it doesn't play a role in determining significant figures. But for my class, you should use this for Avogadro's number, which is 3 significant figures. And now 1 mole of a HCl compound equals Avogadro's number of molecules of that compound. Now, before you pick up your calculator, notice moles of HCl divided by moles of HCl cancel out, and we're left with molecules of HCl. Now, if you looked at your calculator, you'd see this long number. And notice 6.22 is 3 significant figures, 6.02, 3, and 1 is an exact number. Therefore, when you do multiplication division, you ignore exact numbers, but you get the same number of significant figures in your answer as the number that has the few significant figures that you're multiplying and dividing. Both are 3, and you round this off to 3. And that's how you do that type of problem. And here it's similar with atoms of an element and moles, same thing. Now, one of the things you need to know is how to do molecular weights. And if you look at important information, test number 2, and you'll be given this, the molecular weight is the sum of all atomic weights. Now you should see it. All right. The molecular weight is the sum of all atomic weights. So if I were to ask you, what's the molecular weight of NaHCO3? By the way, this is sodium bicarbonate right here. And that's also known as baking powder, baking soda. And what's this molecular weight? I use the initials W for shorthand for molecular weight. We've got 1 sodium, 1 hydrogen, 1 carbon. Notice we have 3 oxygens. So 1 times the atomic weight of sodium to 3 significant figures is this number. For hydrogen, this, carbon this. Now, each oxygen is 16.0, the three significant figures. There are three of them, so I multiply it times 3. Now, when I add it up, I get this number, 84.01. Now, for addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. And the first one has 1, 0 after decimal is significant. Here, 2, 1, 1. The lowest number is 1. So forget about the 84 in terms of rounding off. You only look at to the right of the decimal, keep the 0, use the 1 to round off. Is that 4 or less? Yes, so you drop it. And the correct molecular weight, the three significant figures, is 84.0. All right, let's look at number 9, say 6 or 8 points. How many grams are 5.21 moles of water? Well, what are you being asked to find? Grams of water. What are you given? Moles of water. So this is the only number we have to start with. Over here, my answer, I want the units grams of water. So whatever we're trying to get to, the units go on top of this conversion ratio, grams of water. Whatever we're trying to get rid of, it goes underneath this at the bottom of this ratio. I don't know if you remember, I still do. Top is numerator, bottom is denominator. ND, Notre Dame. Well, I went to Michigan State and we hate Notre Dame. But anyways, that's how we learned it in 2nd grade or wherever. ND. Well, it's still stuck with me. Good teacher I had back then. All right. So where do we get a relationship between moles of a compound water and grams of a compound water? Well, you go and look at important information, test number 2. 1 mole of a compound equals the molecular weight of that compound in grams. Again, 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights. The molecular weight is the sum of all atomic weights. And I see a question I never answered. Flora, I'm not sure when you say what's going on top and bottom. Are you talking about how do I get the units or how do I get the numbers that I put into units?
Yeah, the number that you get in the units,
All right,
like
well,
why is 1 is going in the bottom or on the top? That's
all right.
make me really confused.
Let's go back to the last one, then let me finish this one first. Now, you see here, we're going to use this ratio. 1 mole of a compound equals the molecular weight of that compound in grams. Why did we pick that ratio? Because if you look here, forget about the numbers. Whatever you're trying to get to, you'd put the grams of the compound on top. Whatever you're trying to get rid of, you put that units underneath. So we have moles of a compound to grams of a compound. And that's why we use 1 mole of a compound, in this case water, equals the molecular weight. Shucks, I didn't give you the molecular weight. That's an old word, shucks. But anyways, you have to calculate for this problem the molecular weight of water, H2O. Hopefully you all know water is H2O. And it's got 2 hydrogens, 1 oxygen. The molecular weight is the sum of all atomic weights. The atomic weight of hydrogen, the 3 significant figures, is 1.01. We went through that in the periodic table. And 1 oxygen, the atomic weight of oxygen, the 3 significant figures, that's the number underneath the chemical symbol, 16.0. 2 times 101 is 202. 1 times 1601, or 0.0, I mean, is 16.0. Add it up. Now, remember, after I get a drink of water, you'll have to wait. Remember, when you add things, you get the same number of significant figures to the right of the decimal is the number that has the fewest significant figures to the right of the decimal. 202,022 significant figures to the right of the decimal. 0.01 significant figure. So you round 18.02 to one significant figure past the right of the decimal. Keep the 0, that's your one significant figure. Use the 2 to round off, that's 4 or less, so I drop it. And the correct answer would be, for the molecular weight of water, 18.0. Put it up here, put that. Notice moles divided by moles of water cancel out, because anything divided by itself is the number 1. And here we do the math. You looked at your calculator, you get a long number with a lot of significant figures. This is 3 significant. Oh, I'm in my rut again. Here's 3. Exact number is 1. So you round it off to 3 significant figures. And that's how you do it. Now, after I do the next part or finish with the review, I'll come back and I'll do one of these problems real live on the whiteboard so you can see how I put things on top and bottom. It's also in my videos, but I'll do it again live here. And that should help you out. Now, you're welcome. Now, the last thing I want to talk about is mass calculations for reactions. And an important thing to remember is the coefficients of a balanced chemical equation are molar ratios. If you look on the whiteboard, you'll see a reaction where I have hydrogen gas reacting with oxygen gas to make water. And you can do that. It's expensive, but you can do it. And for a while, that's how they made oxygen or water in outer space if they needed it. Anyways, the coefficient, the number in front, gives you molar ratios. And when there's no coefficient, that means it's the number 1. What this really tells you in this balanced equation, we have 2 moles of hydrogen gas reacting with 1 mole of oxygen gas to make 2 moles of water. Now, the coefficients are exact numbers. The coefficients are exact numbers, but this tells me for every 2 moles of hydrogen that I react with 1 mole of oxygen, I'll make 2 moles of water. And the type of reaction, or not reaction, problem I'm going to go through is I call mass calculations. And I've done many of these on a larger scale when I worked in the chemical industry. How much of this and this do you mix together to react together to make a certain amount of product? And I've worked up to making 180,000 pounds in one batch. For those of you who aren't familiar with that, time out for a quick Dr. White break. Story, or not story, true thing. How many of you have ever seen the vessels or the trucks that deliver gasoline to gas stations? And those are called tank wagons. Let's see if I can get a picture of a tank wagon real quick. Alex, I'll be with you in a second. Oh, you heard Tommy. And if you look on your screen right here, here's they don't show the cab, but this is a tank wagon and they're standardized 40,000 pounds, 5,000 gallons. And if you look at the ladder there, you can go up and inspect inside. And I've climbed those in the winter, check inside to make sure the tank wagon we were going to ship product was clean. I had people work for me, some were sick, and I one time in a snowstorm, it's not fun climbing up that ladder. But with the reaction I was telling you, we made in one batch, one time, I calculated, and I also supervised first time they did it, 4.5 of those. Wow, that was fun. Anyways, back to our problem. Now let's do a simpler one first. If we look at, let me make sure you can see it. Yes, you can. Alex, did you have a question or you just raised your hand that you've seen a tank wagon? All right, if we look on here, mole practice problems part 2, I give you a balanced chemical equation. And if you react 5 moles of C2H6O, otherwise known as ethanol, with oxygen, how many moles of water are produced? So we're being asked how many moles of water, that's why I have the question mark here. We're given how many moles of C2H6O we're reacting. So we can convert moles, this is the only number we have to start with, moles of C2H6O. We're trying to get the moles of water. If I had a ratio that can convert it, I use my good buddy, my good friend, unit analysis. Thank you, Alex. I wasn't sure, but keep an eye out. They're everywhere. But anyways, whatever I'm trying to get to, the ratio the units go on top of the ratio, well, moles of water. Whatever I'm trying to get rid of, I don't want moles of C2H6, and that should be a 6 there, not a 2, on the bottom. And where do we get these numbers? From the balanced chemical equation. When there's no number in front of the chemical formula, the coefficient is 1. When there's no number in front of the chemical formula, the coefficient of 1. So this tells me for every 1 mole of C2H6O, I make 3 moles of water. For every 1 mole of ethanol, C2H6O, I make 3 moles of water. 1, 3. These are exact numbers. And if I do the math, 3 significant figures, exact number, 3 significant figures. Now, this is going from moles to moles. Now, in real life, I can't go out and measure moles. But what I can do is the following, number 4. By the way, 10 points each. Yep, 10 points each for this type of problem. This is a lot of work. How many grams, G is grams, of C3H6, H8, that's called propane. that stuff in the white containers used for your barbecue are needed to make 24.6 grams of CO2. And you're given this balanced chemical equation, which I will give you. You need to do 3 steps. And here are those 3 steps. The first step, whatever compound you're given the weight of, that's mass, you convert it to the moles of that compound. The second step, now that you have the moles of A, you convert it to the moles of the compound you're trying to get the weight to. And now when you have the moles of B, you convert the moles of B to mass of B, which is the weight you're trying to get. Again, let me go through this and I'll show you it in a problem. Boy, this chemistry is thirsty stuff. Anyways, you're going to be asked to find the mass of B formed when you react the mass of A with something else. So whatever you're given the mass of to start with, you convert that to moles. And I just went through how to do that. And second step, now that you have moles of A, you convert it to moles of B. And I'm going to show you how to do this. And the third step, moles of B to grams or mass of B. Remember the coefficients of a balanced chemical equation are the molar ratios. Remember the coefficients of a balanced chemical equation are the molar ratios. So let's do one of these, and there are more I've done in the video, and you have other practice problems. All right, step one, first of all, we're given how many grams of CO2. We're trying to find how many grams of propane are needed to make that. So whatever we're given the weight of, we convert to moles. Grams of this, CO2, we want to go to moles of CO2. Use your good buddy, your good friend. Whatever we're trying to get to goes on top. That's moles of CO2. Whatever we're trying to get rid of goes underneath, grams of CO2. And where do we find a relationship of moles of CO2 to weight of a compound CO2? Oops. You go to important information, test number 2. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights. So 1 mole, and here I need the molecular weight of carbon dioxide. And carbon dioxide has 1 carbon, 2 oxygen, and I sort of did shorthand. Each oxygen is 16, 16 times 2 is 32. 1 carbon is 12, that's the atomic weight. Let me just remind you. The number underneath is the atomic weight underneath the symbol. Remember, use 3 significant figures. If you don't, I'll take off a point. If you don't use significant figures for your answer, round it off properly, I'll take off a point. Now, one thing I forgot to mention, and I better do it right now. Show your work. I've mentioned this before. On these bigger problems now, where you're doing a number of steps, show your work. If you make a math error and then another type of error on a 10-point problem, if you just put down a number and don't show your work and it's wrong, 0 points. Again, if on a 10-point problem, if you don't show any work and it's put down the wrong answer, 0 points. If you show your work and you get the wrong answer, I say, oh, you did that math wrong, made a math error, I'll give you 9 points out of 10. If you got one part wrong, but the rest right, if a couple steps, I can give you partial credit, like 6 or 7 points out of 10, instead of 0, 0. So it pays to show your work. All right, let's go back to that problem. All right, so we found the molecular weight of carbon dioxide, put it in here, 3 significant, 3, 1. Here's our moles of CO2. Second step, remember this is important information, test 2, moles of A to moles of B. What's B? The chemical we're trying to get the grams of. So we have just figured out moles of CO2. Want to go to moles of propane, C3H8. Here's the moles of CO2. We want to go to moles of propane. That's the units of our answer we want in step 2. And you use your good buddy, your good friend, unit analysis. Remember, your good buddy, your good friend, unit analysis. And whatever you're trying to get to, the units go on top of a ratio that you're going to multiply this number to convert it to the units you want. And whatever we're trying to get rid of goes underneath. So where do we find a relationship of moles of C3H8 and moles of CO2? From the balanced chemical equation. Remember, the coefficient tells you molar ratios. And when there's no number in front of a chemical formula, it's the number 1. I like these special effects. Don't answer that. All right, so what this chemical equation, balanced chemical equation is, for every 1 mole of C3H8, you need to make 3 moles of CO2, or 3 moles of CO2 are made when you react 1 mole of C3H8. And that's where we get the 1 and 3. Those are exact numbers, 3 significant figures, 3 significant figures. Are we done? No. We're trying to get grams of C3H8, not moles. And now we do step 3. Moles of B to grams of B. In this case, B is C3H8, propane. So we have moles of propane here that we calculate in step 2. We want to go to grams of C3H8 and use your good buddy, your good friend, unit analysis again. Whatever we're trying to get to goes on top of the ratio, grams of C3H8. Whatever we're trying to get rid of, we don't want the moles of C3H8 in our answer, goes underneath. And anything divided by itself cancels out, so it's gone. So where do we get a relationship of moles of a compound to grams of a compound? Yep, you are right. Important information, test number 2, 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the atomic weight of that compound, or is sum of the atomic weight of that compound. If you go over here, I need to find the molecular weight to get this number of C3H8. And over here, MWC3H8, the molecular weight is the sum of all atomic weights. You have 3 carbons, 8 hydrogens. Each carbon to 3 significant figures has atomic weight of 12.0. Each hydrogen to 3 significant figures, you get that from the periodic table, has 1.01. Do the multiplication, add it up, you get 14.08. Remember, for addition, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. 0.01, 0.082. What's the smallest number? Time's up. hopefully you pick 1. So 0.08, keep the 0, use the 8 to round off. That's 5 or higher. I drop that number in front. I increase by 1, which is 0.0 becomes 0.1. The correct answer is 44.1. And here I do that. 3, 3, 1 is an exact number. And you get 8.20. Now notice I have or 8.22. What's going on? Well, when you do multiple step calculations, there's 2 ways you can round off. One at the end and one at each step. Dr. White is an each step person, but I'm not going to force you to be the way I do it. So I will calculate both ways. Sometimes they're the same answer. Sometimes they're different. Either one, if they're different, would be correct on my test. Like I said, 10 points. And I've got some other problems that you can practice with also. And go back and look at the video where I've done other problems. Well, let's see. Do I have anything more to go over? And the answer is no. So that means I'm done. I'm going to stick around for a little while. If you have any questions, don't forget, show your work on the test, do the practice problems. That'll help you out. With that, I'm going to say, gang gesund. Remember, that means go in health in Yiddish. It's bad out there. The flu is starting to pick up in certain places, I've heard, and COVID is still out there. I still wear my mask. But I'll say gang gesund, and I'll say bye now. Stole that from Granny to Beverly Hillbillies. Bye now.